All right, let's now look at the graphs of the remaining functions that we haven't seen yet, which are cosecant and secant. So I have here, kind of as a dotted line, I tried to make it sort of faint. I have here the graph of sine. The way that we're going to derive cosecant, which is the reciprocal of sine, is similar to how we kind of derived cotangent from tangent. Is just using this graph and thinking about what it would kind of the implications of cosecant being the reciprocal. So cosecant of theta is the reciprocal of sine, which means that obviously cosecant is 1 over sine. So to plot out cosecant, really all that we have to do is take every point on the sine curve. It's really faint, I know, I did that on purpose because this is going to be the cosecant graph. But all that we have to do is just take any point on the sine curve and do 1 divided by that point, and that gives you the corresponding point on the cosecant curve. So let's start somewhere nice and easy with the sine curve, which is, I'd say, right here. Because sine, so this is marked off, each of these units are pi. So this right here is about pi over 2 units. Sine of pi over 2 is 1. 1 divided by 1 is 1, which means that cosecant hits this same point. They agree on that. Sine and cosecant both agree on that point. Well, let's look at some other sort of critical points that sine hits. One, well, there's this right here. So when x is equal to 0, or theta is equal to 0, I guess I could have written these as cosecant x over equals 1 over sine x. When x is 0, sine is 0, which means that cosecant would be 1 over 0, which is undefined. And just like with tangent and cotangent, when we hit those undefined places, that's actually just an asymptote. So I'll draw my asymptote through here. And I'll also draw an asymptote through here because it'll be the exact same thing. Right here at pi, sine of pi is 0. 1 over 0 is undefined. So there's another asymptote here at pi. So wherever sine equals 0, cosecant has an asymptote. And once again, it's the exact same idea. If we just sort of like look at some of these points up here, they're all positive. They're all greater than 0. And as we get close to these asymptotes, sine gets very small. So like right here, where x is just slightly bigger than 0, x is, I don't know, 1 over 1 million, sine, the output of sine is also really small, maybe 1 over 1 million, meaning that at this point, cosecant would be very large. If sine is very small, 1 divided by something very small is something very big. So here where sine is small, cosecant is really big, so there'd be like points up here. And as sine approaches pi over 2, these points get closer and closer to 1, which means that cosecant, as it approaches pi over 2, is getting closer and closer to 1. So it's going to kind of do this. It's going to kind of curve up, sort of make this U shape towards the asymptote. And it'll do the same thing on the other side. Looks like it's sort of like curving in. It's not. So my graph isn't great. I'm not satisfied with it. I'm not very happy with it. It's kind of ugly right now. But this is the general look of it. So at least within this set of asymptotes. But what happens in other places too, right? So like we said, that any time that sine is 0, there's an asymptote. So which is at the multiples of pi. Integer multiples of pi. So there's another asymptote here, but look at what's happening at sine with sine in between these two asymptotes, between pi and 2 pi. Now sine is all less than 0. And again, right here at 3 pi over 2, sine is -1. 1 divided by -1 is -1. So cosecant also hits that point. Sine and cosecant agree right there at 3 pi over 2. And it's going to be the exact same logic as how this sort of branch of cosecant was formed. It's going to be the exact same thing. Take any point right here. 1 divided by that point gives us the cosecant. So this point right here that's like just past pi, it's a really small value. It's negative, but it's a really small value, like negative 1 millionth. The reciprocal of negative 1 millionth is negative 1 million. So it's like way down here. It's very big in the negative direction. And you can do the same thing on the other side, and you're going to get a curve that looks like this. It's sort of like these U shapes. See if I can make these a little bit darker. So now there's a lot going on in this. There's the asymptotes, and then there's the sine curve that I have for reference, and now I'm making these U's, these sort of U shapes. These are the cosecant. And this is what I've plotted right now. That is one period. This is one period of the cosecant. The period of cosecant is 2 pi. If you want a little bit of motivation for why the period of sine and cosecant agree, here's the idea, is that a periodic function is defined for some period p. A function is periodic if f of x plus p equals f of x for all x. And this is the case for like sine. Sine is periodic with a period of 2 pi. Well, okay, if we have some function f for which this is true, f of x plus p equals f of x for all f, then we can sort of divide. This is an equation. This is just an equation, and we can sort of divide through. If I divide both sides by f of x and divide both sides by f of x plus p, then I just get this. 1 over f of x equals 1 over f of x plus p. So if, for instance, if we think of f as being, I'll sort of put it in like brackets here, if we think of f of x as being the function sine of x, here's where we get the sort of like the proof that the period of cosecant is 2 pi, just like it is for sine, because 1 over f of x, if f of x is sine of x, 1 over f of x is the cosecant. So it's showing that for the cosecant, it still has this period of p. So yeah, and I'll just write that, period is 2 pi. And we can keep going sort of in the other directions. Maybe I'll just put one more branch here, just so we can see how it looks. It's just these U's. And the way that I kind of remember what these look like, on the one hand, I just remember that cosecant has this sort of repeated U like look to it. It's just these U's, but you think about, well, where do the U's come from? That's why I kind of plotted the sine curve on here, because the U's come down and they just meet at the peaks and the troughs of the sine curve. So this would look like this. And then there'd be one over here too. It's just these U's all the way down the line. Just kind of like stuck between these asymptotes. So that's what cosecant looks like. How about secant? Well, nice and easy, because we already know that sine and cosine are the same graph, just with a phase shift of pi over 2. In particular, cosine is, if you were to take sine, it's a phase shift of pi over 2 to the left. So it would literally be just taking this exact same graph and just giving it a phase shift of pi over 2 to the left. So this U is going to sort of, it's going to be like right here, kind of cut in half by the y-axis. Which again, you could just think about what the cosine curve looks like. right? Cosine starts up here and it kind of comes down and does this business. It'll be the exact same thing. There's just u's coming off of this peak and trough. Try to make this a little bit darker. Like that. So yeah, maybe it benefits to just sort of think about where these asymptotes are. That's how I think about tangent, cotangent, secant, cosecant. They have asymptotes, and everything is pretty much defined off of the asymptotes. Let me erase this. So asymptotes of secant occur when cosine is 0. When is cosine 0? Is at the odd multiples of pi over 2. So here's pi over 2, and then maybe here would be pi, and then here's 3 pi over 2. So I'm just kind of putting in my asymptotes. And then from there I can plot my little u's, and they just alternate directions. Just like this. Am I still on? Okay. Yeah, just like that. And then over here would be an asymptote at negative pi over 2. That's negative pi over 2, and then maybe it would be negative pi, and then negative 3 pi over 2 is over here. And it's just these little u's that are just alternating directions. And the same thing here. The period of cosine is 2 pi, which means that the period of secant is also 2 pi. So yeah, it's kind of a rough sketch. It's not the prettiest sketch I've ever made, but that's the idea. And then just 2 of these alternating u's forms one period. So if you were asked to draw one period of secant, you just draw 2 of these u's facing different directions. This is like 1.5 periods. So, right, there's that. And as far as transformations, I'll just kind of like say this because it's the same idea as sine or cosine. So the generic form is y equals a cosecant bx minus c plus d. D will specify the midline. A is slightly different in that it's no longer an amplitude, because secant and cosecant, they don't have maximums and minimums. So A with secant and cosecant, it serves the same purpose as it does with tangent and cotangent, which is sort of like a stretching factor. It just kind of takes these and like stretches them out or kind of squashes them down. That's all that A does. B still affects the period in the exact same way. Period is equal to 2 pi over technically the absolute value of B. Same with C. C, it doesn't affect the period, but it still affects like the phase shift. Same thing though, phase shift is given by C over B. It's a phase shift to the right. If C over B is positive, it's a phase shift to the left. If C over B is negative, which is, you know, kind of counterintuitive because there's a negative in here. So yeah, if you see this minus sign, it's the same thing with sine and cosine, that if there's this minus sign in here, it's going to be a shift to the right. If it's a plus sign in there, it's going to be a shift to the left. And then D affects, once again, the midline. It's still the same thing. So the midline of the regular secant and cosecant is the same as the midline for sine and cosine, which is the x-axis. So yeah, D is just going to shift things up or down by however large D is. Okay, so that is the graph. Those are the graphs of secant and cosecant. Let me know what questions you have.